to the talk, Discover the Latest Innovations in the ABAP Language, from Stefan, Gerd, and me. I'm Kilian, and I will start with the session. And this is the agenda of the session. So we will talk about new things in the ABAP language, exciting new things. First, spatial data in ABAP SQL and ABAP. Then we talk about JSON support in ABAP and also Geo-JSON. So these two topics interlap. And then we will talk about random numbers and probability distributions. And at the end, I will give a glimpse, roadmap for the ABAP language, how it will further progress in the future. Okay, so first, an introductory slide. So the ABAP language is a very old, but also very new language. We are simple and modern, and we have an incredibly low TCD. So everybody who knows the ABAP knows this. It is very easy to write ABAP applications and also very complex ones. And of course, we have our built-in transactional programming model, where you can start and write cloud-ready and upgrade stable applications with schema evolution. And of course, you can also integrate new SAP technologies and AI into ABAP applications. And what is very important to us is that ABAP is constantly evolving. So we stay modern. And ABAP is now also an own product area at SAP, so the ABAP language. So you can expect more things to come in the future. Stay tuned, and we will see more in the next years. Okay, so our first talk is about spatial data in ABAP SQL, and it's presented by Gerd, who is from the ABAP SQL team.
Yes, welcome. So what's new in recent version of ABAP 916, kernel and ABAP 2025? We now expose functions of the HANA spatial function library directly in ABAP OpenSQL. There used to be a CDS integration already, so you could store the data, but you could only query the data and call the HANA spatial functions via native SQL functionality. This has changed now. You can integrate and in a single SQL statement, store the business and geospatial data together, which we're going to demonstrate soon, and query it directly in your ABAP program. You don't have to go to the native SQL like these solutions already offered and shipped, like there's a transportation management, utilities add-on you can be able to buy for some years now. And these were all realized using native SQL. They will migrate to stored in a more transparent manner. But if you build something new, you can start with ABAP OpenSQL right away. In addition, which we're also going to demo, the simple transformation support direct import of Geo-JSON data into the binary format. When we talk about HANA Spatial, what we actually need is a flat or curved coordinate system, like WGS84, the GPS coordinate system on an ellipsoid model of the Earth. So you can use it either for map data, also with different spatial reference IDs, or you can use it for a layout of a factory floor or a truck, which you load with data. But it's basically a two-dimensional model on a curved or flat surface. And then you have two additional coordinates you can map onto it, like a Z coordinate and an M property, which are not used for most of the distance calculations. And we expose almost the full functionality of the HANA spatial library. So you can construct geometries, break them apart, point curves, individual points, multi-polygons. You can serialize them as some standard area, also SVJSON to integrate with the GIS solution you already have. You can render stuff, convert from to, and you can compute distances or relationships. We're going to demonstrate some small aspect on it in the demo. And you can transform the data between coordinate systems. Here's an example how you store the data at the bottom. So there's a type in the ABAP dictionary called ABAP Geom EWKB, which is a binary representation of the spatial data, which is basically a blob data on the database, and you annotate it with the target spatial reference system ID. And this allows the data to be directly queried from ABAP and also processed inside HANA. As an example here, now in OpenSQL. So if you're familiar with OpenSQL, you know the @ sign refers to host variables, which you can directly bind here. And you can use type inference to generate the result table. And you can now use the HANA spatial functions as the distance, as the new points. So the spatial libraries are modeled as plain functions in SQL to perform queries on the geometry or construct them from ABAP or load them into ABAP, deconstruct them, extract the coordinates from it. And that brings me to the second part, which I hand over to Stefan Bresch before we go into the demo. We're going to demo both, which is the JSON and Geo-JSON enhancements to the ABAP language.
Okay, so thank you, Gert. So I will continue with the second part. And as Gert already mentioned, we integrated the Geo-JSON support into the ABAP language, especially into the call transformations statement. And there we support the representation or the transformation of data represented in Geo-JSON to the binary format, the extended well-known binary in ABAP. Okay, how we support this in XSLT transformations and in the ID transformation. This is supported via the ABAP type XSD Geo, which is based on the GOM EWKB data type, built-in data type of the ABAP dictionary. And the type definition must be related to a column in a dictionary table where the spatial reference identifier, the so-called SRID, is supplied. For simple transformation, there is additional option by supporting or indicating this transformation by a format option that's called Geo, and additionally, you need to supply the SRID, the system reference ID, that in this case must not be defined in the ABAP dictionary. Okay, then an additional or a second enhancement was that the call transformation now supports source and result JSON. So here we introduced a new keyword JSON that can be specified with the source and result addition. And we support as data format string, xstring, and reader and writer of the new ABAP JSON library. And well, here's an example of how you can write this in ABAP. So you see, well, basically we are serializing a variable of type E or a literal of type E to JSON. And well, this will result in a simple object with an element of with the name I and the value 1. Okay. Well, further to mention is that the symbol transformation itself, they're still based on the JSON XML. So you still have to write JSON XML symbol transformations. And additionally, if you call ABAP methods within your simple transformation, you now can pass instances of the new JSON library to your ABAP. Okay, and the third new thing here is that we have a new JSON library in ABAP for passing and rendering JSON data. And this new ABAP API enhances or replaces the SXML library that was used so far. And well, we provide here new interfaces, reader interface, a writer interface, and also a node type. And we have factory classes to construct instances of this reader and writer. I have a small code snippet here. And yeah, well, we see that what's just a creation of an instance, and then you can, just as with the SXML reader, you can simply loop over all the nodes in this document until you reach the final node. And well, if you find your number node by the name, you can well extract the value of this node. And well, what's changed is that we're not working on the JSON XML, but we are just returning XML nodes, JSON nodes, sorry. And as you can imagine, this is a little bit more performant than the current approach with the SXMLs. We don't have as many ABAP calls for example, for a number or a string. Okay, so these are the 3 new things regarding JSON and Geo-JSON in ABAP. And we will now start with the...
Okay, I hope you have to see the screen. What we're going to display here is a poor man's graphical information system rendering some data from natural Earth, which is in the public domain, depicting the country boundaries of entities in Europe. Some of them as polygons, others multi-polygons. It's a 10-meter resolution database, so it's quite fine granular. And one can see that one can reason now over data in a different manner from just a tabular list of the entities. For example, one can ask the question, what are these islands here between Finland and Sweden in the Baltic Sea? And as an example, we can now, in ABAP and Eclipse, use this graphic information spatial querying system to determine the entity by computing the distance between the point coordinates here, latitude and longitude, in the correct spatial reference ID. That's a flattened WGS84 systems in actual units, and all of them by distance. And if we run this query, it gives us the result. So these islands are the closest shape to this point is Åland, which is an autonomous Finnish territory, similar to Puerto Rico or Samoa for the United States. So it's not completely part of Finland, but associated and listed as a separate entity on this map. And if you look closely, you'll find other things like the Isle of Man or Guernsey, Jersey in this. You may not be familiar with. So this was spatial querying. As a second part, we're going to demonstrate now import of spatial data into the system. And then we're going to use Joule to enhance the service here by more spatial queries to render additional data on this map. And since our product is called Joule, the AI we also use internally for generating and maintaining our code, it's fitting a data set which deals with some. So what we use here is a data set of the maritime observation, which lists all the wind farms which are offshore inside Europe. That's a 500 megabytes file you can download via this request. And inside it, you see it's a combination of geodata, which are your multi-polygons, which can be quite lengthy or polygons, and properties of the respective wind farm, their status, whether it's planned or in production, the number of turbines, if it's concrete already in production, and the power it's supposed to generate was already generated. So to import this data, now we're going to use a simple transformation, which allows us to directly map the data to an ABAP structure and to a table. Let's look at the table. This is the table definition, our target table. We want to import the data in. We flatten the JSON structure, just gave the database names and columns. And we want to import the complete geometry data into a single column, then make it renderable and processable by HANA into a geometry column. And to do this, we use a simple transformation. First, the data table is empty now. This is a simple transformation. We, or the Joule, has written to directly map the data from the Geo-JSON into the HANA database structure. Simple transformation are similar to XSLT. You can transform, and there's the advantage of simple transformation compared to the XSLT support in ABAP is that you can write one single transformation, which you can use both for serializing and deserializing structure. So the ABAP structure you map onto it is.
Es geht über meinen Laptop.
So we map the structure on an internal table in this case, and we can map individual properties and their sub-properties of the JSON. In this case, the whole geometry JSON, which we saw before, with its children, is mapped onto a single database column here and imported into the target reference ID, while other properties are then mapped on their respective columns. And you can see that simple transformations allow you to some impedance matching between the structures, so geometry and property are on the same level in JSON, while the others are actually a level below. But in the target structure, we don't import them into a single table. Let's do this. The class here which does it is a simple HTTP client, which retrieves the data from this URL as a string. And then we call this transformation here with the input. In this case, the source is this character string containing the JSON data, and the result is an internal table, which is directly typed like the database table, and then used to modify the database table directly. So if we run this, that's how it's actually called. And we have inserted 586 wind farms into this database table, which we also see if we then use the data here. So this is a geometry column, and the other attributes are also imported via single call, together with this mapping structure, simple transformation, and the ABAP code. Now let's process this data a little bit further. The goal is to render this data on this map. And if you look at the structure of this, it's all served by a single HTTP handler. And there's actually a mode parameter here which controls what is rendered, the full HTML page, or some layer which represents an individual country. So multiple country map here with the shape of Denmark, if you're familiar with it. And we want to extend this now for a different mode. We want to render the wind farms associated with Denmark, and then blend it into the central map. This is the handler code here. Now, because programming is kind of last decade, to amend the code to render the data from this table. Tool takes everything in context. So we have made sure that the table here is open, the table definition is opened, and We can actually reduce the context a little bit to close the other entities. And we have the HTTP handler code giving us context to Joule. Now, the first rule is AIS be polite, because in 15 years, it's going to boss you around. And the second is give it some hint, which class to use, which table to use. Please extend the handler class. By the geometry data, and the next one, wind farms. By adding amount equal to country wind farms. Sorry, let's make it a little bit larger again. And it should be orient itself how it renders the country map.
Hello?
As a hint. Now let's see what it produced and what it suggests. Okay, so it tries to render here the full class. That's a little bit more than we asked for, because we went say I read this class a month or a year ago. We're going to ask it to display us just the delta. Okay. It suggests to add a method country wind farms to the definition. Sounds reasonable. We have to wait until it's done. Oh, geez. This is a declaration. Then it wants us to extend the method which serves the request by the new mode. You've got the mode country map. Now we should add here the else if. To invoke the method, we just had it generated. And this is a method it suggests. And next. That's it. If we now change the mode here to country wind farms, it represents different shapes, which are kind of in the. That is a proper solution already. And cheating a little bit, fired these requests, but they came back blank. If I now refresh. It actually shows this new geometric data from this wind farm database embedded into the map as different requests. So we see as the planned areas of the United Kingdom, of Denmark, of Sweden, of Poland, and also some Spanish and French or Dutch entities. One can then take it further, which we're not going to demonstrate here. As I mentioned, this is just wind farm data on the sea, which is currently around 40 gigawatts to 50 gigawatts. The whole Europe production is 250 gigawatts, quarter of a terawatt. And China, as you're probably aware of, has twice as much, has half a terawatt, 500 gigawatts. The US is a third with 140 gigawatts currently. About 50 of those in the state of Texas alone. So Texas no longer fuels the United States, it now powers the United States. And the sea capacity of Europe here is dominated by the UK. The green area here represents power produced, and the other major countries are in Germany, Netherlands, and Denmark. And the blue aspect is the area which is currently in build-up. That's not the planned capacity, which we saw before, where lots of these areas are covered. That's what is actually being built today, and the capacity it generates. The current wind farm is no longer your Mission Impossible product from the 2006, I think the movie was. Currently, the record is 20 megawatt wind farm built in China, already productively deployed. And your current wind farm offshore is around 10 to between 10 and 5 megawatt per wind farm. Let's look at the code a little bit more. What we use here is the zoom capability with a viewport. And we do this by using an intersection of the map data with the bounding polygon we compute from the request. Rectangle around it, which is just the bounding box, which is then constructed here in the query. This all is blended into a single result set and then rendered as SVG by the spatial function on HANA directly into an SVG response. And then we color it by the by country color here to be it aligned with the other map. I think this concludes the demo. We'll look a little bit more into power production in the other part of the demo. The 20 megawatts was a peak power. On offshore, you get around 40 to 60% average power. On land, it's a little bit less. It's around 40 to 50%. Okay, and I hand back to Kilian, who's gonna present some more probability and statistics.
Okay, I hope you can hear me. Sorry, we had a little audio problem in the meantime. I continue first with the presentation. I hope you can hear me now better. Yeah, so another small thing which we did, it's only a very minor addition to the ABAP language, is the introduction of probability distributions and their implications to random numbers. And yeah, so up to now, yeah, ABAP had no concept about probabilities as such as a programming language. Yeah, this now changes. Yeah, and this also has some applications for random numbers. So if you look in the ABAP now, you can only generate uniform random numbers, and these occur very seldom in the business context. And here I have an example of generating random numbers representing payment due dates. So you have some bill, and it has a due date when the customer has to pay with some date, and then you want to generate some example data for it when the customers are actually paying. And what you have at the moment in ABAP is you generate uniform random numbers, like on the left, in this example, uniform dates. And this means that at any date, the customers are paying equally likely. And this is, of course, not what happens actually in the real world out there. In the real world, some customers will pay a bit early, some will pay a bit late. But very few will pay very early or very late. And you might get some picture like on the right, where we use the truncated normal distribution to generate this in ABAP. And in the ABAP releases for 2508, you can calculate and generate random numbers with 11 common probability distributions. Yeah, so just to remind you about what a probability distribution is, we will see it later on. In this example, the normal probability distribution, yeah, this blue curve, and you see the value x0, where the density function has its peak. Yeah, this is the mean value in this example. And the probability that some value is in a certain range is actually the area under the curve. And what is very common is this yellow area is the cumulative probability function. Distribution function is the probability that the value is smaller or equal than to x. Yeah. So, yeah. And how to use it in ABAP? It's very easy. Yeah, there is a new system class, a CL ABAP prop distribution. You can use it to create a distribution object like here on top. And then in the next line, we use this to generate 1,000 random numbers. And what is actually new here already is in ABAP up to now, you could only generate one random number at a time. And you had to make a method call for every random number. It's a kernel call and it's expensive. And now you can generate like 1,000 of them at once. And you have to put some uniform random number generator as a RNG parameter. And then it generates some normally distributed random numbers. And with this class, then you can also compute some common attributes of such a probability distribution, like the mean or the median or the variance. You can compute the cumulative distribution function, which is like the probability that the value assumes is smaller than or equal to 1 in this example. You can calculate the blue curve, this density function here with this PDF or PMF call, or you can compute the quantile, which is the opposite of the CDF. With this, for example, you can answer the question, at which date do 95% of the customers have paid their bills? Yeah, that would be the quantile. And if you generate these random numbers there, you can get, if you make a histogram, you will see some graph like this on the right, which resembles the bell-shaped curve, which we saw before in the example. Of course, not exactly because, it's of course, that's only, Okay. You can also do things which you could do before better. For example, if you want to generate integers, there is the uniform int distribution, which is also part of this class. You could also do that before with CL ABAP random, but you can do more here because the constructor of this class accepts a range table. And so you can, for example, generate all numbers from 0 to 10 except 5. And not only one of them, but like 100 at once. And of course, this is much faster than before. So please take a look at these new classes. They might come in handy. And what we also did to implement this class is to introduce some new functions into the ABAP language. So these are basic numeric functions, like the other numeric functions, what we already had, for example, exp or sin or whatever, sinus and exponential functions. So we now have the error function, which actually gives the probability function of the density function, the probability cumulative distribution function of the normal distribution. We have the gamma functions, which is used in many different probability distribution, which you can see on the right. And we have some basic combinatorial functions, which is factorial and binomial. You find them in any programming language out there, and now you can also find it in ABAP. And it can be used like all other functions in ABAP, as you can see here in this small code snippets. So you can compute the factorial of 1,000. So of course it can use the DEC float 34 range here. If you don't have a calculator which can calculate with that high numbers, you can choose the ABAP from now on. Okay, so I come to a little demo to show the probability distributions, and I also use the nice example of Gerd with the wind park data. And what we want to have at the end is this little app here on the right, so a little web app which simulates like the current power which is generated from the different wind parks grouped by country. So in the green, you see the total power output of the wind farms. And on blue, you see the currently generated power. And we do this by generating random numbers, of course. And exactly by simulating how much wind is blowing. And then we have also some probability that wind turbines may fail. And then we have the actual number of broken turbines. And of course, all this influences how the current power output is. We will see this in the code. Yeah. And for this, we will use these three probability distributions here. On the left is the Weibull distribution, which is normally used to simulate wind speed. Yeah, you see we have some peak here. And so it's not very probable that there's no wind. So at the beginning, this curve is quite steep. And at the end, it's flat. Of course, very high wind speeds are unlikely, but of course occur in practice. Yeah, then we use the beta distribution to compute the wind turbine fail probability. So this returns some values between 0 and 1. And you see, yeah, so I said that 0.1 is like the average. I don't know, when I was driving through near wind parks, I always see if there are 10 turbines, one of them is mostly out of order. So I assumed that here. And then I use the binomial distribution, which is very common. If you throw a coin, for example, it's 1/2, 1/2 for both sides. And if you throw 10 coins, it gives like the probability that you have like 3, 4, or 5 successes. And this you can use if you have the wind turbine fail probability. This is what you can use to actually compute the number of broken turbines in a wind farm. Okay, now comes the demo. I show a small piece of ABAP code, which actually gives this nice web app we saw before. A little moment. So I hope you can see it. So of course, first I have like a little method which gives me a simple power curve of a turbine, which if I assumed here, if the wind is very low, then we don't get any power from the turbines. If the wind is between 3 and 12 meters per second, we have a linear increase. Then over 12 up to 25, then we have the max power output of the turbine. And over 25, we cut down. Yeah, it's too much wind. And in practice, there's also a cutoff where the wind is stopped. Yeah, and then we simulate the wind speed. And for this, we use this Weibull distribution, which is not yet supported by the classes here, but we simulate it. We will show it in 1 second. It has 2 parameters. The shape is used for wind simulations, normally with the value of 2, and also in the science. And then we calculate the second parameter of this distributions is the scale. And we calculated that it increases with the distance from the coast and is an average 9 meters per second plus some scale factor times the distance. And then we can compute this random number here by drawing using this new system class and draw a number from the exponential distribution and multiply it with scale and shape. And if you do it in that way, we generate Weibull distributed random number. So with this, we have the wind speed. And then, of course, we compute the number of working turbines. So we first get a random number, how much wind turbines are broken. We draw this from the beta distribution here, similar as before. And then we use the binomial distribution to get, so we get a fail probability. And from the binomial distribution here, we get the number of broken turbines in the wind park. We draw here a random number. And of course, the number of broken turbines is, so the number of working turbines is the number of turbines minus the broken turbines. And with this, you can simulate the output of the farm, that you first get simulate the number of working turbines with the method above. Then we get the total power of the working turbines. Then we simulate the wind speed. And then from the wind speed, we use the power curve to simulate the power of the turbine and can return it. Yeah, and here above, you see that I select from this table and then loop over this and simulate the output per farm. And this is then aggregated with the group by here. And at the end, I've wrote some vibe coding with Joule, which gives me this web app, what I show you now. Actually, it generates some SVG. And let's see how this works out. So at the end, you get this little web app. And if you click here on repeat, you'll see that the random number generator is working and generates some realistic numbers, which according to Gerd is around 40 and 60%. And you can see it's mostly true. Yeah. So, and it's very funny what you can do actually in ABAP now. Yeah, a kind of realism. Yeah. So we have wind random numbers distribution, which is also used in science for that, and dependent of the distance from the coast and so on. It's quite nice. Okay, so this was the demo of the random numbers and the probability distributions. And now I come back to the slides. Okay, I will show a small glimpse of the ABAP roadmap. First, a little disclaimer. So, of course, what is normal with roadmaps, you cannot rely on it. So they can be changed by SAP at any time without prior notice. We are still in the way of finding many things here. What we plan very early is like the new SQL merge command. You all know that we in ABAP try to leverage all functionality of the HANA database. And in ABAP, there is select and update and modify and delete and with as ABAP SQL statements. And we now want to introduce also merge as a new statement, which is a more powerful version of the update statement. So what also comes is some new concept of generic structures. You know all generic types like any, data, or C sequence in ABAP. You probably also know that there are generic table types like type index table, type hash table. But up to now, there are no generic structure types. And that's a big thing which is missing in the type system. And we are working on this. I show an example in 1 second. What we also plan to introduce is a true Boolean data type with 2 values, true and false, like in any other programming language out there. And we also show something in that direction. And of course, these generic structures might be some glimpse that we are doing more in terms of genericity in ABAP in the future, but what we do there has not really been decided. So here is just an example of the generic structure. So the syntax and everything might change. You can see here a method, and this has an importing parameter of type any structure containing field 1 type EI and field 2 type I. So this could be some syntax which defines a structure which contains these 2 fields, but you don't know where they are at the beginning or the end, and how many additional components there are. Yeah, so this is the type of structure genericity which we plan to introduce. And then you can write many things which you could only done with dynamic programming before statically, and this also will be much faster. And a second one is that we plan to introduce a Boolean data type, which the plan type name is B, with values true and false. And as you can see in the code snippet below. So and last but not least, so this was it with our talk here. You can find on the links more about ABAP Cloud, about the other sessions at the Devtoberfest and the sessions at Subteket. And I hope you enjoyed this session as well. Although the sound quality was not perfect in the middle. And I'm looking in the chat if there are some questions. Okay. Gerd corrected me about the wind power curve. So if there are any other questions, you can put them in the chat. Else, Mamike, perhaps we can then close the session if there are no questions anymore. Okay.